Welcome to Chapter 3, Section 6, Implicit Differentiation. We're going to take a quick look at how we differentiate functions that aren't explicitly defined. And let me tell you what I mean. In the past, we've had y equals some function, and so y is explicitly defined as a function of x. And we can differentiate that using all of our power rules and our product rules, quotient rules, and chain rule and all that. Well, what if we are implicitly defined, meaning that y is not set equal to some function of x? There's y and x intermixed. And let's look at a simple implicit function of just y squared equals x. Now, if we were to solve for y here, we would actually get two different functions, positive radical x and negative radical x. And it wouldn't really give us what we're looking for here. So we can use what we know from the chain rule, and we can find the derivative here. And what we want to do is we still want to take the derivative of everything with respect to x. And we're going to do that to both sides. And as you know, the derivative of x with respect to x is just 1. So you expect to see that we're going to get 1 on the right side of the equation. But what do we get on the left? Well, on the left, we get the derivative of y with respect to y times the derivative of y with respect to x. And if we take a look at that, we see that this 2y is simply the derivative of y squared with respect to y, and the dy dx is the derivative of y with respect to x. And if we notice, the dy's cancel, and that's just taking the derivative of y squared with respect to x. So we're left with 2y dy dx. All right? Now, we want to find dy dx. We want to know what is the derivative of y with respect to x. And so we just solve. We divide both sides by 2y, and we get our function dy dx is equal to 1 over 2y. Now, you might want to pause a second here and think, wait a minute, this is a derivative with y with respect to x, and it doesn't even depend on x, it only depends on y. And that's actually not a problem. In fact, that is very helpful if we look at the graph of the function. And this is the graph of the function y squared equals x. And notice y is not a defined function of x because it doesn't pass the vertical line test. However, this is the graph of y squared equals x, and we notice at any given point, any given x value, we have two different tangent lines. So let's say, for instance, we had the x value of 4. Well, the slope of the tangent line does not depend on x. It depends on, well, which y value are we talking about? Are we talking about 2, or are we talking about negative 2? And so if you plug that in, 1 over 2 times 2 is 4, so it says this slope of the tangent line right here is a positive 1/4. But if we're talking about this point down here, then it's a negative 1/4. So this derivative right here is, in fact, very helpful for this type of implicit relationship. Okay, let's take a look at another one. Let's take a look at x cubed minus y cubed is equal to 6xy. And in fact, this is number 14 in section 6 of your book, one of your homework problems. So we're going to take a derivative of this with respect to x. So we want to take a derivative of the entire relationship here, both sides of the equation, with respect to x. So let's do that. Derivative of x cubed with respect to x is just simply 3x squared. The derivative of y cubed is 3y squared, but then we have to have the dy dx. Remember, this is the chain rule, because 3y squared is really the derivative of y cubed with respect to y, but we're taking a derivative with respect to x. So that's why that dy dx pops out. And on the right side, we notice we've got a 6, but we also have the product rule here. So we want to take the derivative of the first times the second, so that's just going to be a y, and then plus the derivative of the second times the first, so that's going to be x dy dx, because the derivative of y with respect to x is simply dy dx. Now at this point, we have to do a little bit of algebra, and we want to get everything together here. Okay, so if we distribute the 6 in through here, we're going to get 3x squared minus 3y squared dy dx is equal to 6y plus 6x dy dx. And I'm going to notice I've got a positive 6x dy dx over here, and I've got a negative 3y squared dy dx over here. So I'm going to put those on the same side and say that's simply a 3y squared plus 6x, that quantity, times dy dx. Now I'll let you figure out to make sure that those signs are correct. If you move the negative 3y squared dy dx over to the right, they are both positive. I just wrote them on the left because I like to have my variable I'm solving for on the left. Now we move the 3x squared over to the other side as well, and so we're going to have a 3x squared minus 6y. And so I want to solve for my dy dx. That's what I'm trying to look for ultimately, is what is the derivative of y with respect to x. So I want to divide everything by this quantity that I have as my coefficient. So I get dy dx is equal to the quantity 3x squared minus 6y all over 3y squared plus 6x. Now we can simplify this slightly to say that we can take a 3 out of everything, and so we're left with x squared minus 2y all over y squared plus 2x. And that is my derivative of y with respect to x. So let's try to summarize things a little bit here, and let's look at the process of implicit differentiation. And that's what we're doing here. This is taking an implicit equation of x and y, and we're taking the derivative implicitly. And in both of these two examples, we followed this same four-step process. First, we take the derivative of both sides with respect to x, and we do the product rules, quotient rules, any rules that may come into play with differentiation, and we collect all the terms with the dy dx on one side of the equation. So anything that has that dy dx that pops out, which will happen when you take a derivative of a term that has a y in it, we take all those and we put them together on one side. We factor out the dy dx, and then we can solve for dy dx. And it's the same process. We're using all the same rules that we used in the last section. We're just going to take the derivative of implicit equations now instead of explicit equations that we've dealt with thus far. Let's take a look at one more example here. And this, in fact, is another one of your homework problems, number 24 from page 220. And we have cosine of xy is equal to y, or you can write it as y equals cosine of xy, and we want to find what is dy dx. Okay, well, to find that, we've got to take the derivative of both sides with respect to x. So we do that to the left and to the right. Nice thing is, on the right, we get a dy dx, so that's simple enough for us. But over here on the left side, the derivative of cosine is a negative sine of our angle xy, but then we have to take the derivative of the angle xy, and that's our product rule. So we multiply by the product rule where we get y plus x dy dx. Okay, and looking at this, we want to once again get all of the terms that have the dy dx over on the other side. Well, we notice we have a 1 dy dx on the left, but we're also going to have this negative sine xy times an x dy dx. So we need to get that over to the other side. So this is going to be a 1 plus x sine of xy times dy dx is equal to, what do we have left over? Well, this product of negative sine xy times y, so that's a negative y sine xy. Now, I know I skipped a couple steps there algebraically. I'm going to leave it up to you to make sure that makes sense with your own way of thinking. And now we only have one more step to solve for dy dx. We want to divide by this whole quantity. So dy dx is equal to a negative y sine xy all over a 1 plus x sine xy. And that is our derivative. And notice this derivative is in terms of both x and y, but our function is in terms of both x and y, so that kind of makes sense. You know, if our function depends on what both x and y are, then our derivative is going to as well.